Hello everyone. Today we are doing some housekeeping. Let's talk through the overall plot or vision for self-driving development with the simulator. Today we discuss how everything hangs together. What is our objectives and what is achievable? What are the key problems we need to solve and skills we need? What are the main building blocks and how we solve key problems? What things we need to consider before we start? So hopefully we'll get some answers to those questions as we go today. The objective of today is for you to be able to develop your skills based on this and work within this framework, but do it at your own pace. And at the end of today, you'll see a high-level overview of what's involved, what the objectives are, and so on. So let's talk about our main goal. Although generally on this channel, what we're doing is developing our skills in multiple aspects of autonomous driving. That's basically what this channel is all about. And there are many things that we've done so far. We did some neural nets and computer vision. We did some basic geometry, and recently we are doing reinforcement learning. But how do we define our main goal, and what can we realistically achieve here? So I've been thinking about this, and this is how we can define our main objective. We need to develop a good model to control a car navigating from point A to point B with a good level of traffic around it. And this model can only just use one vision camera. That is generally it. Of course, you can also leverage side cameras if you want, but for now, I'm using one front-facing camera for simplicity and purity of the challenge. Okay, that's our main objective. Let's define it a bit more and go into how we solve it. We are building a model, and any model has inputs and outputs. Our inputs is mainly front camera footage, but maybe the current speed reading as well, and we'll discuss it later. Our outputs are car controls being sent to the simulator, steering, throttle, and brakes. That's quite simple and understandable. And our outcome from all of this is the car getting from point A to point B. How do we do it? Say we focus on reinforcement learning as our main tool for this. And let's recall one of the most important aspects of reinforcement learning and why we use it. It allows us to develop our model in a very iterative step-by-step approach. And what we mean by that is we can gradually change our environment and the rewards logic from the very basic to more sophisticated. It basically allows us to force learning certain behaviors at a different stage, hence the name, reinforcement learning. Cool. So in reinforcement learning context, our input into the model becomes what is called observation space. This is what the car gets from the simulator. And our output is what is called action space. The controls that we get from the model to send to the car, where to steer, to what extent we press accelerator, and if we brake or not, and to what extent we brake. For observation space, generally it is simple. We use the current frame of the camera footage, which is a 3D array. And each of those 3D dimensions is like width of the camera footage, the height, and third dimension is the RGB values, or red, green, and black values of the pixel. However, recently I've been thinking that we need to add current speed as well, and we need to find how to add it to our array. And that is something that we need to solve, as our stable baseline 3 RL library does not actually allow us to send two objects in the observation space. So we need to combine it into one. For action space, on one hand, our direction is easier. We need to make sure we declare all three up front: steering, throttle, and brakes. So that is quite simple. But on the other hand, we may need to move from discrete values that we've been using now to more continuous number space to represent those. So the steering could become more precise and the acceleration could become more precise. So we have defined our inputs and outputs for the model. Now, the next thing we're talking about is our success criteria. So we get the model going and make it take the car from point A to point B in a simulator. But we need to measure how we measure that success. And I suggest we use the following 5 criteria. Number 1 is there shouldn't be any collision, especially with pedestrians. That is quite obvious. Number 2, the car needs to obey all traffic rules. Number 3, it needs to complete the route as much as possible, or at least to make maximum percentage of the route complete. Number 4, it needs to do it quick enough, so it can't get stuck in one place or going too slow. And the last one, number 5, is also kind of very important. It needs to do it in a very smooth way, or in a smooth enough way so it doesn't shake the hell out of your passengers in the future. So that's our success criteria. The way we implement it is by using rewards logic in our model. Whatever we want the car to do or not to do at a certain stage, we encourage or punish by rewards. The two main problems to solve here are, number one, making sure you balance your rewards well to be the most effective enforcing the right behaviors. And number two, because you need to grab various simulated telemetry to calculate your rewards, you need to ensure not to slow down your training process, because your reinforcement learning episodes and time steps can be, million time steps at a time. So you need to grab all of that lane information, intersections, traffic lights, speed limit, collision sensors, and so on in a very efficient way so you don't slow the simulator or don't crash it. So these are the two issues to deal with, at least in the reward space. The next important thing in the reinforcement learning context is solving navigation. I've done a few examples in the past, but not all the way from point A to point B. Yes, you need to have a complete route, how to get from point A to point B, and you can also give rewards progressively as the car gets along your route. That's the easy part. The problem is this: you can't give it an angle to the next waypoint directly. That would be like cheating. That angle is what the model needs to figure out given the image in front of it. You need to think about it in the context of navigating, like in a real car, navigate using Google Maps. And Google Maps is not being updated for the latest road changes that you have in front of it. This means the car needs to drive around what it sees, but eventually get from point A to point B. And that's what you need to solve here. You kind of need to figure out a way to disconnect navigation from what the car sees, because in real life, those things could be different. The next set of tasks in building reinforcement learning model is where you need to use your creativity. They are all around making it easier for the model to figure things out. Example, how we simplified camera footage by running it through some convolutional neural network. We were forcing the model to see lane markings and road surface in general, but we were simplifying the actual representation of that array into a much smaller object. We also needed to generate some training footages to build that model. So each one of those things that you do in reinforcement learning could become a separate rabbit hole, but you need to solve those rabbit holes. And the quicker you become at solving those problems, the quicker you get your model to do the right things. Before we finish, we need to mention things you need to get right at the very beginning. And there are three of them. The first one is testing your model against reality at some point. And probably the easiest way to do it is to grab your model and get a real Tesla footage from somewhere and then apply your model to it. And you can do it on just the computer, so you don't need to, mount any cameras in any cars or anything like that. But then you also to figure out how to view that footage with your model applied, because you need to maybe create some flexible arrows that will just nicely overlay over the footage so you can judge how well your model predicts where it needs to go and how well it shows what the throttle and braking should be and things like that. The important consideration here is to make sure your camera footage looks as close to what you going to be testing against in the future, right? And that's why I'm generally trying to calibrate all my cameras on real Tesla Model 3 footage. So that's number one, because you need to begin with the end in mind. So one of your aspects is you need to be able to test it against reality, meaning that in the most practical sense, getting some real footage from a real car is the way to go. And if it happens to be some other brand or model of the car, by all means. As long as you have access to it, you just need to make sure you calibrate your camera to look in the same or give you as close footage as possible. And of course, there are two aspects of that. The positioning on the car needs to be kind of in the same spot, but also the field of view or focal length. So those things is what you need to get right. So that's number one before you start. Making sure your camera footage look exactly the same, some real camera footage from a real car. Number two is your observation space. You need to decide if you use RGB or semantic camera, that's one. And secondly, you need to decide whether you add in current speed. If you make those decisions up front and solve how you add the speed to it, you will save yourself some time in the future, which is what we're trying to do here. And then number three is your action space. Just you need to make sure you don't forget that you need to have all three dimensions from the very beginning. You need to have your throttle, steer, and brakes. Otherwise, you start with the steer and then you need to add your throttle and you need to start from the beginning. So make sure you have all three at the start. And that's pretty much it. That was an end-to-end overview of all tasks you need to solve at a higher level to build a reinforcement learning model for an autonomous driving car in Carla Simulator. As usual, thanks for watching. Please subscribe and share. Safe driving.